The largest eigenvalue of a symmetric matrix maximizes the Rayleigh quotient. But what about the second eigenvalue? The third? The Courant-Fischer theorem reaches every single one of them with a max of a minute, and the proof turns on one-dimension count. The setup. A is symmetric, so it has real eigenvalues, which we order from largest to smallest, and an orthonormal basis of eigenvectors, Q1 through Qn. The tool is the Rayleigh quotient. Written in the eigenbasis, R of x is a weighted average of the eigenvalues, with non-negative weights that sum to 1. We derived this identity in the last video. An average never exceeds its largest ingredient and never dips below its smallest. So the maximum of R is lambda 1, and the minimum is lambda n. The interesting question is how to reach the eigenvalues in the middle without knowing a single eigenvector in advance. The Courant-Fischer theorem, lambda k is the maximum, over all k-dimensional subspaces S, of the minimum of the Rayleigh quotient inside S. Read it as a game. You pick a k-dimensional playground. An adversary then picks the worst vector inside it, the one with the smallest Rayleigh quotient. The theorem says, the best playground you can possibly build scores exactly lambda k. Half 1. Exhibit a subspace that scores lambda k, span the top k eigenvectors. Inside that span, the Rayleigh quotient averages only the top k eigenvalues, so it can never fall below lambda k, and it equals lambda k at qk itself. The max of the min is at least lambda k. Half 2 is the heart of the proof. We must show that no k-dimensional subspace does better. Whatever S you build, the adversary can find a vector in it whose Rayleigh quotient is at most lambda k. Here is the hinge. Let T be the span of the bottom eigenvectors, from qk down to qn. Its dimension is n minus k plus 1. Add the dimensions. K plus n minus k plus 1 is n plus 1. That exceeds n, and two subspaces whose dimensions sum past n must share a non-zero vector. Every playground S contains a witness from T. And that witness is bad news. Living inside T, its Rayleigh quotient averages only the bottom eigenvalues from lambda k down. An average of numbers at most lambda k is at most lambda k. Put the halves together. Every subspace's score is at most lambda k, and the top eigenvector span achieves it. The max of the min is exactly lambda k. Every eigenvalue of a symmetric matrix, characterized by pure optimization, no eigenvectors required. There is a mirror image. Applying the theorem to minus a, whose eigenvalues are the negatives in reverse order, turns every max into a minute. Lambda k is also the min over subspaces of dimension n minus k plus 1 of the max inside. A numeric check. For a random symmetric 4 by 4 matrix, we sampled 50,000 random two-dimensional subspaces and scored each by its minimum Rayleigh quotient. The best score landed just below lambda 2 and never once exceeded it. The eigenvector span hits it exactly. First payoff. This defines each eigenvalue by optimization alone, with no characteristic polynomial and no eigenvectors. And because the definition only mentions subspaces, it lets you compare eigenvalues of two different matrices, which no determinant formula does cleanly. Second payoff. Perturbation theory. Add a small symmetric error e to A, and min-max shows every eigenvalue moves by at most the norm of E. That is Weyls inequality, and it falls out of this theorem in 3 lines. Next video. Third payoff. Singular values of any rectangular matrix obey the same min-max law. Apply Courant-Fischer to B transpose B, whose eigenvalues are the squared singular values, and take square roots. The complete logic. The top eigenvector span scores lambda k. Any other k-dimensional subspace must intersect the bottom span T, because the dimensions sum past n, and the shared vector caps that subspaces score at lambda k. Remember, the kth eigenvalue is the best possible worst case. Build the best k-dimensional playground. The adversary's answer is lambda k. And the whole proof is one-dimension count. K plus n minus k plus 1 exceeds n.